Hello again, and welcome to another review session for your Calculus 3208 final exam presented by CDLI. We're moving right along now, getting into more detail with applications of differentiation. And another rate of change sort of situation that you might see that is a common application that you can apply the concepts of rate of change and derivatives to would be something called population change. You can model how populations are changing, but it could be populations of just about anything, as we will see. So let's get right down to business. Key topics that we're going to look at today will be on population problems, and then we'll think about how we can apply that to other growth and decay situations. And let's talk about this monster that we call population change. It says a common application of derivatives is this study. So for a population function p of t, which represents basically the population of something as a function of time t, the first derivative of that is what we call the growth rate. So the rate of change, usually we think about growing populations, and if you have a negative growth rate, you have a population that's in decline. And we can also think about the second derivative as having some meaning. It's really the rate of change of the growth rate. So it tells you, based on what we know about the growth rate, whether or not the population is increasing or decreasing. And if you look at what we have on the bottom there, when we compare the growth rate to its rate of change, we can learn a little bit more detail about it. So let's say we have a positive p prime, a positive growth rate, but it turns out that p double prime has a negative. So basically, although our population is growing, the rate at which it's growing is starting to sort of level off a bit. And if that's happening, we call that a stabilizing population. Or let's say that p prime is positive, and not only that, but our growth rate is increasing because the second derivative is also positive. What that means is that our population is growing, but that the rate at which it's growing is increasing. So that gets out of control very quickly. We would call that an unstable population situation. So that's just another way to look at that. The same sort of thing can be happening with populations that are in decline. If you're declining and the rate at which you're declining is getting more and more, then you're going to have an unstable population. If your signs are the same, they're both negative. Okay? So opposite signs for the first and second derivative. We have stabilizing population. The same sign, unstable, because it's getting out of control. It's a bit analogous to what we talked about with our linear motion in the last session, because when we saw that velocity and acceleration had the same sign, we're speeding up, but when they had opposite signs, we're slowing down. Well, this is the same kind of thing, only instead of motion, we're talking about growth. The signs are the same, the growth is speeding up, and if they're different, then the growth is slowing down, which means things are stabilizing. Okay, that's enough wordiness. Let's get down to some business. So here's our first example, a bacterial colony. So there's one kind of thing we can have a population for. A bacterial colony is being studied under certain conditions intended to control its growth. Now, normally when we talk about growth and decay of something like bacteria that usually grow or decay really quickly, we get an exponential function that models that. But in this case, it says it's under certain conditions that are intended to control its growth. So we're still growing, but it looks like we're modeled by a polynomial function here. So the population is in hundreds of bacteria of the colony after t hours. So time is measured in hours, and p is measured in hundreds of bacteria. So under these conditions, this is our equation. What is the growth rate of the bacterial colony after 24 hours? So let's take a look at part A. So what's our growth rate after 24 hours? Well, that's pretty straightforward. We just want to find what's our derivative at 24. So the first thing we need is a derivative equation. So we can say p prime of t will be 24 plus 14. And that was a simple derivative to take. Quadratic became a linear. So then we have that p prime of 24 will be 24 plus 4 times 24. Okay, so we put all that together. It's the same as having 5 times 24, which will be 120. So we should interpret this in terms of the problem and give it the correct units. So we're going to have a growth rate of 120, and remember that's in hundreds of bacteria. So, and it's a positive number. So what that tells us is that we're growing by 120 hundred, so 12,000 bacteria per hour. Okay, so we're growing by 12,000 bacteria per hour, at exactly 24 hours after we start the experiment that we're doing here. All right, let's take a look at part B. It says, is the growth rate increasing or decreasing at this time? So for that, we're going to have to look at our second derivative, P double prime of T. And our second derivative, if we think about it as just differentiating this one, is going to be just equal to or. Okay. And it says, is the growth rate increasing or decreasing at this time, and by how much? Well, it's increasing because that's positive by an extra 400 bacteria per hour. So what does all that mean? It means that we're growing at a rate of 12,000 bacteria per hour, and then the next hour, so let's say we can approximate it if it were linear, an hour later at 25, then we'd be growing by 12,400. Did my addition wrong there? 12,400 bacteria per hour. So every hour, not only are we growing, but the rate at which we're growing is going up by an additional 400 bacteria per hour. Okay? So that's how we can interpret that. An interesting thing about this, as long as this function keeps increasing, which it will do, and note here that the population, the second derivative, is also positive, then this is always going to be unstable. So even though there's something going on in this experiment to try and stabilize the population, it's not working very well. All right, next example. The population of a small town in rural Newfoundland changes based on economic conditions, mortalities, and birth rate. So those are pretty much the same factors that affect populations in almost any town under normal circumstances. And it says the table below gives selected values for the population over a 20-year period. Okay. Now let's take a look at this table carefully together for 1 sec before we start to do anything here. You'll notice that if we look at the increment in time, 1994 to 2000 is a span of 6 years, and then it goes to 2002, just 2 years, and then 05 is 3 years later, and then another 5 years, and then 2 years again, and then 2 years again. So what we can see here is that this data is kind of sporadic. So we can't just read the values of P and look for patterns because they're not normalized, because we haven't got that constant increment. Okay, so the table below gives selected values for the population over a 20-year period, and selected they are. Use estimates of P prime at 2012 and P double prime at 2012 to describe how the population is changing. Okay, so let's figure out an estimate for this one first, and then we'll get an estimate for this one if we can, and then after we've got those two things, we'll see if we can understand something about how this population is changing. So let's start with, first of all, trying to find an estimate for P prime at 2012. So the rate of change of the population at 2012. Well, we have seen lots of different ways to estimate the slope at a particular point if all we have are data. And one of the things that we can do is just pick another point that's close to it. And so there's one that's close to it. If I take this 2010 with its population and then 2012 with its population, the slope of that secant line that we could think of would be an estimate. And another one we could use would be using 2012 to 2014, going this way instead of that way, and that would give us another estimate. So let's use the 2012 from 2010 as our first estimate here. So we're going to say that the rate of change of our population in 2012, one method of estimation is to use a secant. So let's go with 340, that's 340 people, small town it said, minus 345 in the previous year, divided by what we've got is 2012 minus 2010, because it's a 2-year span. And so that's going to give us -5 over 2. So we're going to say that our population is about equal to, our population change is going to be about equal to, we're losing about 2.5 people per year. I don't know how you lose a half person. Ha ha ha. No, these things are estimates, of course. So our population growth is actually a population decline in this case, and we're losing about 2.5 people per year in that stage. Now, that's if we measure that secant. And the second thing we want to do here is get an estimate for the second derivative. So if we think about this one as being on the left side, let's use the estimate on the right side as being another estimate that's just to the right of that. And then we'll try to get an estimate for our second derivative by finding how much we change from our first estimate on the left to our second estimate on the right. So let's do another one. So let's say we'll call this our estimate for 2014. So P prime in 2014 could be about, we're going to need another one so we can get our second derivative, of course. So this is going to be about 337 minus 340 divided by 2014 minus 2012. And so what that tells us is that we have negative 3 over 2, or about 1.5 people per year. Okay, so in 2012, we're losing 2.5 people per year. And then in 2014, that's an estimate, of course. And in 2014, we're estimating that we're losing only a rate at about 1.5 people per year from our small town. So if we wanted to get an estimate for the second derivative, we could use those two and find out their rate of change over that 2-year span that we're talking about. So let's try that. Let's get an estimate for our second derivative. And that's a trickier thing to do. And the more estimation you do, less and less accurate things get. But you do your best with what you have. So let's try another one here. We're going to say that the second derivative at 2012, we can use those two values that we had before. It's going to be about equal to, so we'll say negative 1.5, subtract negative 2.5, divided by the span of time between those two things. So 2014 minus 2012. And so what we end up with in our numerator here is actually a positive 1 over a 2. Okay, so what that means is the rate of change of our population change here is going to be about 0.5 people per year So despite the fact that our population is declining, we have the opposite sign here. We have a positive for our second derivative estimate. So we have to interpret all this. Well, what I would say is that the population is declining, but not getting into control. It's stabilizing because we have those opposite signs there. Okay, so that's how we do a question like this if we were asked to interpret it in the context of a numerical example where we had to estimate everything. Okay, a little bit trickier, not too bad. Alrighty, so here's the your turn question. So it's only a quick session this time, not a whole lot here. So the your turn question talks about coyotes that were introduced to a national park in an effort to control the rabbit population. So a population database produced a model for the rabbit population each year since the introduction, which is represented by that. Okay, so it says use the values of P prime at 5 and P double prime at 5, so just some derivatives and second derivatives to calculate, and to see what it predicts about rabbit population growth and stability 5 years after the introduction of the coyotes. So take some time to work that out. Pause the video if you like. And here's the solution to the your turn question, worked out in all the gory detail. So it turns out that the population is still growing, but it is stabilizing. So maybe the coyote stuff worked. I don't know. Alrighty, let's take a look at a quick summary of the things that we said here. So what we said in this section was that population as a function of time, P of t, and the first derivative represents your positive growth or decline rate, and the second derivative represents the change in the growth rate and gives information about this magic thing called stability. And population models can be used to model anything from human population to bacterial cultures and wildlife, the 3 examples that we saw here. And they're also a very common application of differential calculus. But they could also be used to model pretty much the number of anything that's going to grow or decline. So any kind of thing that we have to look at a growth rate or a rate of decline. It doesn't even have to be a population specifically. Okay, so I hope that shed a little light on another application of differential calculus. And I hope your studying is going well. Good luck.